Hello, welcome to this Math 125 calculator tutorial. In this video we are going to be running a two-variable analysis of this set of data that we see. So to begin, we want to enter data into our calculator. If your calculator is not in stat mode yet, you're going to have to put it into stat mode. If I just hit data right out of the gate, I see that I have a stat error. So I'm going to clear that out. I'm going to hit second, and then I'm going to hit data, and the calculator wants to know, am I doing a two-variable analysis or a one-variable analysis? So I'm going to put it in the two-variable analysis. Now I'm going to hit data so I can start inputting my data. If you already have data listed here, then we can clear out our data by going back into stat mode. And if you go to the right, there's an option to clear data. So that would be an easy way if you're doing multiple problems at the same time to just reset that data list between problems. Okay, let's go into data and I will put in the data that we see here. Well, our first x value is 41, so I'll type in 41. Then I'm going to hit the down arrow and I'm going to type in the first y value, which is 6. Then we hit the down arrow again and I'm going to type in the next x value, 33, I'll hit down to type in the second y value, which is 20. Then we go down and we repeat, so 18 for x, 23 for y, 37 for x, 8 for y, 36 for x, 12 for y, 18 for x, 26 for y, 30 for x, 28 for y, 17 for x, 13 for y, 26x, 18 for y, 40 for x, 9 for y. So once we finish this last item, you can just hit enter, and we are now ready to run our analysis. So if we hit the stat VAR button, then it will calculate our two-variable statistics. First of all, it will tell us how many values we have plugged in, which is 10. We could verify that by just counting the number of rows in this table. I've gone through the process of plotting this scatter plot in a spreadsheet, so we can kind of just see what the data looks like. It looks like we have a negative trend in our data. We would say that there's a negative correlation. It doesn't appear to be particularly strong, and we'll see that once we get over to some of these numbers that we've computed. So the calculator has computed the number of values we plugged in, so I'll just say that n is equal to 10. This will be a number that we reference later on when we're thinking about critical values of our Pearson correlation coefficient. It also computes the average x value, the sample standard deviation of x, the population standard deviation of x, the average y value, sample standard deviation of y, the population standard deviation of y. It computes several things that we aren't really interested in a Math 125 class, but eventually, here at the end, A, B, and R are going to be the three items that we really kind of hone in on when we're doing this two-variable analysis. So I'm going to start with R. R is our correlation coefficient. So we can say this is negative 0.638. If this was a negative number, it means the correlation should be a negative correlation. If it had been positive, you would have seen a positive correlation where the two variables were increasing together. If this number is close to 1 or close to -1, so I should say if the absolute value of it is close to 1, then it's a really strong correlation. If the absolute value of this number is close to 0, it's a very weak correlation. So when we looked at the scatter plot, we said it wasn't particularly strong, and when we look at the number, we would also say, yeah, this isn't that close to 1. We use these English words to describe correlations, but we aren't going to assign a particular R value to any one of these. In this case, I think it's safe to say that we have a moderately strong correlation. Okay, the equation of the linear regression is written as y hat equals ax plus b. You can compare this to a very kind of famous formula for an equation of a line. That's the slope-intercept form of a line. Y is equal to mx plus b. And in fact, they're the same. So a is taking the place of our slope. B is the same thing. It's our y-intercept. And instead of calling the the dependent variable y, we're going to be calling it y hat. The reason we put a hat on the y variable is just to indicate that if we ever actually use this for predictive value, the answers we get were not y values in the original data set. They are y hat values, which just indicates that they are values that the model predicted. Okay, so our equation is y hat is equal to ax. Well, let's figure out what a is. We'll go over here. A is equal to negative, let me put this off a little bit, negative 0.53. I'm just going to use 2 decimal places of accuracy. X plus, right, so that's ax plus, and now we'll go find out what b is. Moving over here, I see it's 32.10. 32.10. Okay, this equation may be useful to make predictions, but it may also not be appropriate to actually use the equation to make predictions. How do we know if we should or should not use this equation? Well, it's based off of this Pearson correlation coefficient. If your number is really close to 1, you can probably use this. If your number is not very close to 1, you probably shouldn't use this. But when I say that, that's very ambiguous. So there's actually a table of critical values that your R value needs to surpass in order for us to say that the observed correlation is statistically significant. Now, there's a couple of things that go into this. One of them is that the question is going to have to designate a significance level. The significance level is you can think of it as the percentage chance that the assertions we make about the data are not correct. So looking at a significance level of 0.05, we would say that if we have met this significance level, then there's a 5% chance that statements we make are not correct. Now, you can imagine that people might not be happy with a 5% chance of making a mistake, so there are multiple significance levels. You could even have significant levels that are weaker than 5%. If you are okay with a 10% chance of making a mistake, you could consider alpha to be 0.1. Or if you want to be really confident in your results, we might strengthen this and say alpha is equal to 0.01. This is typically something that a researcher is going to designate ahead of time. In any given problem, we don't pick the significance level. It would just be given to us, and then we would have to decide whether or not this equation is useful at this significance level. Okay, in order to do this, we're going to have to keep in mind that we have 10 data values and we have this 0.05 significance level. So as we look at the table, what we're going to see is we're going to see different n values. We need to focus in on 10, and then on any given row, there's going to be two different values depending on if we had a 0.05 significance level or a 0.01 significance level. In our text, we aren't really going to consider significant levels that are different than these two, although in theory, you could pick any significance level, 0.02, 0.03, etc., but these are definitely the two most common significant levels. Okay, so we should be looking at this number 0.632. Now we're going to compare our R value to this, and specifically we are going to compare the absolute value of our R value. So we're going to drop the negative sign, and once we do that, we get 0.638, And we can say that the observed correlation is statistically significant if the R value is greater than the critical value. So you look at these two numbers and you're like, hey, this R value is a tiny bit closer to 1 than this critical value, and that's all that is required for us to say, yes, the observed correlation is statistically significant. All right, I hope this video has been helpful in utilizing this basic scientific calculator to compute this Pearson correlation coefficient, this equation of the linear regression, and then a little bit of that discussion about what are those critical values of the Pearson correlation coefficient.